Today we begin the real study of quantum mechanics now that we are done with the mathematical preliminaries, and we will begin with a very quantum mechanical experiment. It's called the Stern-Gerlach experiment, which was conducted in 1922. And this lecture is adapted from a book titled Modern Quantum Mechanics by Sakurai. The book is at a higher level and it's not so easy to read for anyone, not just undergraduate students. But I think my lecture will be simple enough. The Stern-Gerlach experiment is a classic experiment that cannot be explained using classical, that is quantum, not quantum mechanics. So what did Stern and Gerlach do? They sent a collimated beam of silver atoms through an inhomogeneous magnetic field and detected the beam at the other end. Their goal, somewhat misguided, was to understand something called space quantization, which was used by Bohr and I guess Sommerfeld. And anyway, this experiment also shows why one should report what one sees rather than what one expects to see, unlike our attitude in BTech lab. And sadly, I think it did not win a Nobel Prize, even though Stern did get it for something else. So let's do some chemistry. So the silver atom has atomic number 47, and its atomic structure, it's got fully filled orbitals until 4d10, and so the thing is that it could get 4f1, but actually it fills 5s1. I think if my memory is right, it's something called Hund's rule or something. So another way of understanding the atomic structure is that the inner part is like Kr, it's a noble krypton, and then you have 4d10, which is a fully filled shell, and there's 5s1. The total orbital angular momentum L of all the 47 electrons is 0. And so the electrons, however, carry another form of angular momentum called spin angular momentum. But 46 of the 47, all these guys which are inside the square bracket, are all paired up, and so they don't contribute anything. So the only source of angular moment of any kind is the unpaired electron, which is sitting in the 5s orbital. And so S here we'll use the symbol S to denote spin angular momentum, like we use L for orbital angular momentum. By orbital angular momentum, I mean it's R cross P. So in problem set 8, we saw that a particle of charge Q, mass m, and orbital angular momentum carries a magnetic dipole moment, which is given by Q upon 2m, where Q is its charge and its mass m times its angular momentum. In the silver atom, we saw that the total angular momentum of the electrons was 0, so hence there is no magnetic dipole moment due to orbital angular momentum. However, as I explained, electrons carry another kind of angular momentum, and so just using this formula, a formula like this, and replacing L by S, we get a formula like this. And as we put in a fudge factor or a constant factor, it's called the Landé G factor. And so it's G, which is some unknown factor, E upon 2 me, me is the mass of the electron times the spin angular momentum. So it's conventional to measure spin angular momentums in units of h bar. So what we do is we multiply and divide by h bar, and this quantity Eh bar by 2me that we have is called a Bohr magneton. So suppose the spin angular momentum was 1 in units of h bar. That means the magnetic dipole moment would be 1 Bohr magneton if G was 1. Okay. For electrons, one can derive from something called Dirac equation that G equal to 2 up to small corrections. In fact, G minus 2 is one of the most precise quantities measured that match theoretical predictions. Okay, so the conclusion for the takeaway for us is that the silver atom is neutral. It carries a magnetic moment proportional to its spin angular momentum. The rest of the chemistry is not so important at this moment. So now let's look at a force on a magnetic dipole. Okay, so one thing we know is that there will be no magnetic force if the field is homogeneous. That means it's constant, uniform everywhere. However, it's not true if the field is inhomogeneous, that it varies in space. In problem set 7, we actually worked this out. So there's a magnetic dipole M in an inhomogeneous magnetic field B. We saw that the force was m dot del. This is a scalar operator acting on B. And so let's, for simplicity, assume that the homogeneity is along the z direction. Then the force along the z direction will be Fz, which would be, and B we are taking to be only a function of z, so it will be just some mz, dz, bz, all the other derivatives. This thing, so that this we can rewrite as mz is nothing but m times cosine of the angle theta with respect to the z-axis. So you get something like this. So the force is proportional to cosine theta, and the force will be positive whenever cosine theta is positive, and negative direction, z direction, when cosine theta is less than 0. Of course, this cannot be the only case, because we know that del dot b is 0, and del dot b is dz, bz plus other stuff, so there must be other things. And I mean, of course, we know how to handle that complication, but at your level, we will ignore that. So here's a photo of Stern and Gerlach. And so this is taken from this article, which is in red here. If you go to the slides when I share it with you and click on it, you will get a link to that thing. So these are the two people. This is a Stern's photo from 20, and this is Gerlach from 1911. So let's look at the Stern-Gerlach setup. And this again I've taken from Sakurai's book. So you have an oven. It's around 1000 degrees centigrade. You heat up silver atoms, they'll come out of here through a hole in the oven, and then you have a collimating slit. I think Stern and Gerlach had 2 slits, and then you send it through a magnet, and then from whatever comes out you have a detector, a screen of sorts where you detect. So this is it's a very simple, it's a tabletop experiment. Okay, so this is taken from Stern and Gerlach, How a Bad Cigar Helped Reorient Atomic Physics. It's a must read. Okay, so this experiment, even though I mean Stern was an expert in many things, took them a year to accomplish. In the final form, a beam of silver atoms was collimated by 2 narrow slits of width 0.03 mm and traversed a deflecting magnetic 3.5 centimeter long with field strength about 0.1 Tesla and gradient fairly big, 10 Tesla per centimeter. And the splitting of the silver beam achieved was only 0.2 mm. Accordingly, misalignments of collimating slits and their magnet by more than 0.01 mm was enough to spoil the experiment. And at the end of the day, only a meager film of silver atoms, too thin to be visible to an unaided eye, was deposited on the collector plate. And then Stern described what happened, and that's where the bad cigar comes in. So they were not seeing anything, and Stern they didn't have lots of money. Most academics don't. So they were smoking cheap cigars. And so he was smoking a cigar and looking at the plate, and he just let off the cigar smoke. And cigar smoke has sulfur because it's a cheap cigar, and silver became silver sulfide, and all of a sudden they were able to see the pattern of silver being deposited. And of course they went back and fixed their experiment so that they could use this sort of effect in an automatic fashion. So now let's ask, what should one see on the screen? So without a magnetic field, all the atoms will appear in the middle of the screen, and there'll be a width depending on the kind of slit they're coming through. And the magnetic dipole moment of the silver atoms will be distributed isotropically, as there is no preferred direction. So let's assume that there is some directionality given by the fact that it's coming from one direction, and we'll call that the y direction. And let's kind of assume they are of constant speed u. We can handle the case when there is fluctuations in this number, but let's for simplicity assume there's a constant speed u in the y direction, and we will expect a z deflection in the z direction proportional to cos theta. You can work out the details of how this would happen. So now what will happen to the beam will spread out, the force being different for different atoms. That's the cosine theta. But there could be also other effects due to non-zero z components of the initial velocity of the atom, and we also neglected a few other things. So now this is like the simplistic picture. So here the horizontal is the y, and the vertical is the z direction. And so the beam comes and it gets spread out, and you get some kind of profile. This is what we expect. Okay, classically, because the force is proportional to cosine theta, so it will give you some spread, even if all of them were in one beam. So I'm just redrawing the figure here. So the same thing, this is what we expect. But what was observed was more like this. two nicely separated profiles with nothing in this. But again, these profiles, by the way, don't take them too seriously. They're just supposed to be caricatures. Okay, and so these two are quite distinct, and clearly this is not the same as this. And so this is the key observation of Stern and Gerlach. So the actual photo here is from their plates, and so this is without a magnetic field, so there is some kind of vertical distribution. But then you observe that when a magnetic field is switched on, it opens up and there's a gap in the middle. And so of course we understand this whole structure, but from our viewpoint, you just focus on the middle thing. You see that at Z, if you stick to the middle, you see that there are two such profiles, one here and one here. Here is a detailed description of this, but for us at this moment, we are just focusing on these two ends. The fact that there's nothing in between. So what we are doing is a slice in this direction here. Okay, so this is the conclusions from the Stern-Gerlach experiment. The dipole moment appears to be taking only two values, not a continuum of values. See, as Z was going to be m, the Z component would be m cosine theta. So it could take any value from minus m to plus m, but it's taking only two values. And Stern and Gerlach estimated the magnetic dipole moment of the silver atom was 1 Bohr magneton to 10% accuracy. So this is what they're able to get. So they measured the thing and you fit it to that formula. So we don't know what G is. So of course they didn't know about spin angular momentum, and they assumed that they proved Bohr's idea of space quantization. Today's space quantization refers to the outcome of the SG experiment. And it was only in 1925 that Uhlenbeck and Gutschmidt actually considered that the electron could have spin. But with 20/20 hindsight, which all of us have, and we know about spin and the Landé G factor, we can conclude that the electron carries half integral spin in units of h bar. So Sz would be plus or minus half h bar. Okay, so that's what it is. So it's in units of h bar, it's just plus or minus half. Now it's very important, this half is not some random thing. The half integral value of Sz is in sharp contrast with orbital angular momentum. It takes on only integral values. And what this says is that one cannot and should not visualize spin angular momentum by modeling the electron as some, in a small, very, very small size spinning top. That is a completely wrong thing. Spinning tops can only have integral angular momentum, even if they are quantum tops. So this concludes our description of the Stern-Gerlach experiment. And a boring conclusion would be, yes, they measured the magnetic moment of the silver atom and they got two values. Okay, but now we will what we're going to do is we're going to refine this experiment and ask us what it can teach us. Okay, so in some sense, if you remember, when we looked at polarizers also, we did things like we put sequential polarizers. So it's really in the same spirit that we're going to do this, and pretty soon it will be clear what I mean. So let us first summarize the basic SG experiment. You have an oven, and then you send from there you send some atoms. They went through this magnetic field, this thing, and you got two components. We'll just call this the SZ plus component and the SZ minus component. That was the two splits that we got. Okay, but there's nothing special about the Z-axis. We can just do a 90-degree rotation of the magnet, and that will become oriented now in the X direction. And again, there is nothing special of Z versus X, so we should expect to see the same thing, Sx plus component, Sx minus component. Okay, so these two are the same thing. Okay, so now let's try a sequence first. So the sequence is as follows. So now we want to make an analogy with polarizer. So we have an oven, and SGZ, like this, would have given SZ plus and SZ minus component. What we do now is we block it. So this blue thing here says that I've blocked the thing. Now it behaves like a polarizer. It's blocking one of the guys, and only one is coming through. Okay, and we send it through a second HGZ polarizer. And what do we observe? What we observe is that there's just an SZ plus beam and no beam here. So this is exactly what we did. Compare this with Z polarizer. So you sent a thing which had both Z. So remember, we had in our polarizers Y was our direction of propagation, and the polarizations were in the Z and X plane. So we sent something which was like E1 EX cap plus E3 Ez cap, and it goes through the Z polarizer. What did the Z polarizer do? It projected out the Ex cat component and sent through only the Ez component. But the second guy did nothing. That's what this is telling you. So in some sense, the analogy is there. So we can identify Sz plus beam with polarization, linear polarized beam along Ez cap, and the blocked out guy Sg minus we can identify with the linearly polarized beam along the X cap. It's just analogy. So we have Sz plus beam, Z polarized light, and Sz minus X polarized light. By that I mean linearly polarized light with polarization along the X direction. So now comes, can we push the analogy further? So we vary things. So up to here we just done, so this is just our, like the analog of the Z polarizer. We send in SGZ and block the SZ minus beam and let the SG plus beam go through. It goes through this, and what you get, okay, is that you get again two. You get a SX plus beam and SX minus beam. Okay, so this kind of suggests that the SX plus beam in some sense contains both these guys. Okay, so now let's do something which is now a sequence of 3 before we understand this. So so first two are the same as above, but now what I do is I block the SX minus and send it through SGZ, and lo and behold what I get is SZ plus and SZ. I get 2 peaks in this thing. So now how does this work? What does this mean? So look at it this way. Here we kind of saw that we blocked the SG minus thing, SZ minus guy, and so it goes through this, and if this were not there, and if I put this thing, I would have only got a SZ plus beam. But what is happening is that once I introduce this SGX in between, it's actually this beam, it says that as, of course it's in analogy we can say that the SX plus beam should contain this, but it also kind of shows that that this is doing something different, that these measurements don't commute. Okay, this is similar to polarizers, they also don't commute. So ordering matters where you put things. So viewing SGZ as measuring 2 possible values of SZ, we see that measuring SX messes up the measurement of SZ. It conflicts, that's what it's doing. So see, what entered here was a thing which had a proper well-defined SZ value, and what came out here did not have well-defined, it has a combination of both. So this is roughly the set of experiments. So now we can do one thing. So SGX, so we're going to look at this SGX after we do the blocking. We have blocked the bottom guy. Okay, so let's try to understand this. And so SGZ, after blocking, it looks now, let's look at this. We send E3 EZ plus E1 EX through Z polarizer. This will project out this E1 part, and you get E3 here. And when it goes through the polarizer, pi by 4 polarizer, even though what we sent in was polarized along the Z, now we get a linear combination of Z and X with same strength. So now this behavior is exactly like here. So it's saying that this beam, if you think in terms of SZ, is exactly similar to the pi by 4 polarizer. Okay, so again we will use the analogy, and we think of SZ as a linear operator on a 2-dimensional VS with orthonormal basis SZ plus SZ minus. Okay, so we just think of these as not, I mean classically we would have said okay, spin up and spin down, but what is happening here is that we can create situations where we have linear combinations of these guys. So we can do that in a linear vector space. And so in this basis SZ will be diagonal. For the plus guy it will give H cross by 2, and H bar by 2, and SZ minus it will give this thing. And so this guy we will just write as H bar upon 2 by sigma Z. Some books even use capital Z for this matrix, which is just 1 and minus 1. So now the question is, what is SX? But we can look at this. SX should be SZX, which we saw here, should be, where is that? Yeah, here, SZX. This was giving something which was equal components of both. So we can just say that the state, which is with SX plus, is some linear combination, and we have a lot of freedom here. We put 1 and 1, we say take them to be 2, and divided by root 2. This is just to make this a unit vector. These two are unit vectors, so if you take which are orthogonal to each other, and this thing. So now Sx acting on this is h cross by 2, Sx plus by 2. So this is just the statement that this state has well-defined Sx and it is plus h cross by 2. So now, of course, there should be a state which is Sx minus. So now question is, how do we do this? And we use the fact that Sx plus and Sx minus should be orthogonal to each other. And little thought, I mean, there's freedom in signs, but I'll just use a convention and put a minus sign here. So now we have a basis in which so if you act with Sx on this guy, it will give you minus h cross by 2, the same thing. So it's another way of saying it. These two are eigenstates of Sx, just as Sz plus and Sz minus are eigenstates of the operator Sz. Eigenstates or eigenvectors. So what is the matrix for Sx in this basis? You can just go back and use our definition of matrices. You will get h cross by 2, 0, 1, 1, 0. And this matrix up to this factor here, prefactor, is called the poly sigma x matrix or capital X. So now, but the point is we can have y also. We just, for simplicity, we are doing z and x. What about sy? To obtain this operator, we will choose the spin LVS to be an LVS over complex numbers. Over reals, we really don't have space. And so what we do here is almost similar to what we did for Sx, except we put an I. This is something which we can do because we are over complex numbers. And so this is just a guess. Don't take this beyond that. And so these are the analog of basis vectors that we use for circularly polarized light. If you remember, there was a minus. Remember, Sz plus was like E3, and this is like E1. So E1 plus or minus I. These two guys would be like circularly polarized light. And if you work out the matrix for Sy, it's again h cross by 2, 0, minus I, 0. And this matrix, after you strip it of the factor of h cross by 2, is called the sigma y matrix, or just some capital Y. So let us now conclude. The SG experiments show that Sz can take two values, plus or minus h cross by 2. Sequential Stern-Gerlach experiments suggest that it's possible to create a spin state where linear combinations of Sz plus and Sz minus are possible. For this to make sense, we consider the two-dimensional LVS, which is the C of two possible states plus and minus. So remember, we had seen how to convert a set to a vector space. And with this On basis, Sz plus for corresponding to plus spin, and Sz minus corresponding to this minus. So this is a two-dimensional complex vector space. In this basis, the three components of spin are represented by linear Hermitian operators, this is important, given by h bar by 2 times the Pauli matrices. Okay? So one might wonder, of course, x, y, and z, there nothing special about them. What about, if you give me, what about the spin operator along n hat direction? And I'll just write something without proof. Just say that this object n hat dot s, this would be this projection of spin along n, is just h cross by 2 n dot sigma. So you think of the three Pauli matrices as a vector of matrices, and then you get this thing. Then you can actually go ahead and show that this works in the sense that its eigenvalues are plus or minus h bar by 2. And further, you can also show that this is nothing but a unitary transform of the Sz guy. Okay, where U is the matrix of eigenvectors. Okay, so I will be sharing some notes on Moodle, which also has a detailed description of eigenvalues, eigenvectors, and anglicization of matrices. So kindly read these remarks in that context. And you should, and the conclusion of this thing is to remember that even though we would have thought of spins as being continuous variables, first thing Stern-Gerlach is telling us is that, look, it can take only two values, but there is this weird configurations which correspond to neither up or not down, but some linear combinations of them. And so we argued that you have to describe the quantum state of a spin as a vector in a Hilbert space. So the next lecture will move on to the postulates of quantum mechanics, and we will use the spin system as a very important example to illustrate the basic ideas, and maybe we'll do a little bit of generalizations and before we proceed. Okay.